Conceptual design of the Ventus V111. Design brief and baseline configuration.
The mission profile follows the AVD design brief, where the missed approach leads to a second cruise at a chosen altitude of 25,000 feet at a Mach number of 0.63. These values were set by calculating the optimum cruise speed and comparing similar aircraft with similar mission profiles. The loiter speed was set to 209 knots.
The V111 has low-mounted wings for greater structural performance and easier engine maintenance. It has dihedral to improve lateral stability and sweep to address transonic compressibility effects. However, these characteristics reduce aerodynamic efficiency and increase weight. The aircraft also has two efficient high-bypass turbofan engines positioned under the wing. Despite the risk of FOD due to low engine clearance, this allows the span loading to counter lift loading while producing minimal aerodynamic disruption. The aircraft also has a conventional tail chosen for its structural efficiency and a tricycle undercarriage with multi-bogie main landing gears for ground stability and handling.
Initial sizing.
The takeoff weight is the sum of four components: crew, payload, fuel, and empty weight. Crew and payload combined create a fixed weight of around 26 tons based on FAA weight recommendations. The empty weight and fuel weights are expressed as weight fractions.
Using linear regression of similar aircraft data, the empty weight fraction is estimated by a power equation with constants A, 1.05, and C, minus 0.0641. We can validate our results as they are similar to the estimates made by Raymer.
Using the key assumptions illustrated in Table 3, the fuel weight fractions associated with each of the 9 mission segments are found as highlighted in Table 4. It is important to note that the most efficient loiter is at the calculated maximum lift-to-drag ratio, whereas the most efficient cruise is at 86.6% of that maximum, as explained by Raymer. The Bragg range and endurance equation are then used to find the fuel weight fraction for any cruise and loiter segments respectively. The others are estimated using regression data from Raymer or Roscam. Note that the descent to loiter and later descent to landing are assumed as one descent segment. Finally, assuming a 1% allowance for trapped fuel, the total fuel fraction is estimated as 0.33. The takeoff weight and empty weight fraction are found by solving a pair of simultaneous equations graphically. The intersection of the curves plotted in Figure 4 gives an empty weight fraction of 0.492 and a takeoff weight of 144 tons.
Overall, we have great confidence in the validity of our estimate as it is in between the Boeing 767-200ER and A321XLR. From Raymer, the typical jet engine SFC values for loitering cruise were chosen. These values are valid as they are similar to modern engines such as the LEAP 1A or the Pratt & Whitney 1100G. The aspect ratio for jet transports is given as 7.5 to 10 in Raymer. We decided to go for a high aspect ratio of 10.5 because modern aircraft have higher aspect ratios due to more efficient structures, better materials, and better winglet technology. Additionally, the A321XLR, an aircraft with similar mission parameters, has an aspect ratio of 10.5, which further supports our decision. From Raymer, the ratio SWET over SREF of 6 was chosen as it fits the civil jet transport range. No or minimal use of composite materials was decided, as experience from designs such as the A350 showed disappointing weight reductions due to electronic requirements, such as grounding points for internal wiring.
Sizing to constraints.
The constraint diagram is used to choose thrust and wing area which meets performance requirements. Starting with field performance, an empirical relation for balanced field length was used based on Raymer. For landing, an empirical formula was used assuming no thrust reversers or speed brakes. For the next constraints, CD0 and Oswald efficiency are required. Our CD0 value was first estimated to be 0.016 based on a statistical method by Roscam. However, we were not confident in this estimation, so we used a value of 0.02 based on similar aircraft.
It is found from Thornbeek that turning performance is a useful constraint for maneuverability but not a regulatory requirement. For max speed, the specific excess power equation assumes maximum true airspeed is attained at cruise altitude. The stall speed constraint was not included in the diagram as it is imposed directly on the landing constraint and there are no constraints explicitly given by FAR 25. Calculating the absolute ceiling constraint and assuming constant thrust with velocity sets our IVX to be our minimum drag speed. For climb besides FAR, we included a direct climb constraint to ensure the aircraft can reach cruise altitude. Climb and takeoff were found constrained the most. Empirical formulae were used in landing and takeoff, which should be recalculated using a physically based formula as design progresses.
The design point is selected to be at a wing loading of 5,350 Nm² and has a thrust-to-weight ratio of 0.29. We wanted to minimize the thrust-to-weight ratio while trying to obtain the average optimum wing loading for cruise, which is found using the Bragg range equation and cruise speed. The average optimum wing loading at cruise was found to be 5,270 Nm², which is lower than the minimum thrust-to-weight wing loading of 5,350 Nm². We are confident that choosing a slightly higher wing loading is a good compromise for obtaining a lower thrust-to-weight, especially since the optimum wing loading is just an average of the entire cruise segment.
We considered the takeoff and landing constraints at a CLmax of different HLD combinations. Slats and plane flaps give a CLmax of 2.45, which is too constraining. Slats and Fowler flaps give a CLmax of 3, so the design point can be met. However, we selected slats and single-slotted flaps with a CLmax of 2.7, giving a minimum thrust-to-rate ratio close to the optimum cruise wing loading. It is therefore the least complex HLD combination, which still meets our desired design point.